All right. So yeah, like I was saying, like this stuff, like the neural networks in general, I think are some of the really interesting things of like what we can do in machine learning. It's kind of like, in my opinion, it's kind of like it's so crazy how simple in a way it is. It's obviously not just simple just for like, oh, you put a bunch of things in there and just let it run and it's automatically done. But basically, if you think back on like linear regression, you have to like tweak every part of the model and make sure you have the right features and stuff like that. Neural networks are a little more flexible, and the way you pay for that basically is large computation. It's kind of expensive too. And when I say expensive, I mean like computationally, like takes a lot of computational power, which means more time for it to actually run through. So you can technically basically create any kind of mapping, train anything on a complex enough neural network, but realistically, it might not work, right? Like it might just not, and when I say not work, I mean, it takes too long to train and doesn't ever reach its global minimum versus in the cost function versus a local minimum, where basically it finds a good enough answer, but not the best answer. So we're kind of like, technically you can always find the best answer, but there's some mathematical reasons why. So we're going to kind of talk about that a little bit today. So let's see here. Making sure I have everything that we have. So last time we talked about, we actually did a Keras implementation, right, of the neural network. Okay, so like I said, Keras is one of the one way to implement it. There's also basically through PyTorch. TensorFlow is kind of like similar way, though Keras is actually can be built into TensorFlow to connect it, which is kind of interesting. Those are just other libraries and frameworks you can use. So just kind of know that those exist. But what we're going to do today is I'm going to go ahead and start sharing my screen. And I'm going to show you basically when you actually implement these parts. And I kind of suggested this last time when I was showing the Keras implementation. You might have noticed when I actually put things together. Maybe I'll share that part real too. Okay, cool. So you should be able to see my screen now. And I'm going to make it a little bit bigger so a little bit easier for me to interact with too. So let me go ahead. That's a bit better. Okay, cool. So I'm going to go back to just real quick the Keras implementation. And remember, this is all on GitHub, right? All this stuff, so you can always go back to it. But if we go back to our implementation, we actually created the neural network. You'll notice that when I actually did the model compile, I did a few things. For example, I defined the loss from here, which is basically a categorical cross entropy, which is like the log. If you remember, we saw the log within, I think it was in Learn, but basically like how we identify. But you'll notice here too is optimizers. So we can actually do some extra stuff here. In this case, this optimizer basically do something called stochastic gradient descent. We'll talk about that today. We define our learning rate. We define the momentum, which we'll talk about too. And then we also have Nesterov, basically is a different kind of optimization, which I think the curriculum shows a whole bunch of different parts. I'll have a link to a blog post. I think that shows a really good example or goes through a whole bunch of different optimization stuff. But basically the reason why we do these optimizers is that we want to make sure that our model actually converges to a global, or not a global, but basically a good enough minimum in the cost function. We want it to be a good enough function. Now that doesn't mean you're going to get the best function. It's possible that there is a global minimum that's just really hard to get to, but we don't want something that's like basically just guessing or not a good enough model. And this is some ways we can do basically optimization and basically increase it. So, but before we even talk about optimizations, we have to talk about like overfitting. So one issue with models is that we say, oh, if they're not complicated enough. If they're not complex enough, they're just never going to encompass enough stuff. And that's what we call underfitting, right? So one issue though with neural networks is that we can actually do the opposite, which is overfitting. And we talked about overfitting before, but the main idea here is that basically your model uses the training data essentially too well and just essentially, like I like to imagine, it likes to memorize the answers without generalizing. And that's kind of what overfitting really comes down to. So we want to make sure we don't overfit it. And so one thing we kind of been doing before, we have to have a train test split, which kind of helps us make sure our model doesn't actually use just the training stuff. But this actually comes into a little bit of an issue, is that we don't actually want the test during the process of training. We actually will do something called a train validation and then a test set. So the way you can imagine this is if we have this large data set and we basically would split up into different parts. The majority of the data will be our training. We want most of the data to actually train it. And then we'd save about, you know, like maybe 5% of the data, maybe even less than that, for testing. And that's basically, a lot of times we'll call it a holdout test, where we literally don't use any of it, any of the process, and we only use our train and validation data, which is basically like this other set, and we'll use a train to basically push through our model, basically feed forward, and then test it against how well it goes, and go back and forth, back and forth, back and forth, and we'll do our validation to say, okay, how well is this data that's not being trained on, but how well is it matching? So this is kind of a subtle point of like why we have this train and validation, but we'll kind of go a little bit more. So one thing I kind of think of it is like, I think of like training is like when you're studying for a test. So it's kind of like you get the material you have together and you study for a test. The problem is if you use literally your training for your tests, you're gonna have an issue, right? Because then you're just gonna memorize everything and not really understand the material. So your training idea is basically you want it to train and understand the material well enough. So your validation, I like to think of it as like your practice tests. It's so like you basically say, okay, like you make your own practice test, or maybe your teacher gives you a practice test, right? And says, okay, like you basically train on the material, right? Like you study the textbook and everything like that, and you have a practice test. So like at the end of, after you kind of learning everything through, you do a practice test. You wouldn't start looking at the practice test while you're studying, right? But basically this is to gauge your knowledge on how well you're doing after you're basically studying or training, okay? And then at the very end, we actually have our testing set. And our testing set, oops, okay. Our testing set basically is more like our, what's it called? Like our final thing. It judges how well the student is. In this case, our student would be like a model. So this actually allows you to use a testing set that you've never seen before and judge not just your model, but you could also judge multiple models. So you can think of like actually creating different like tweaks of your model, training and validating it with the training and validation set. And then at the very end, testing and saying, okay, which one actually performed well? And the idea here then is basically have a completely unbiased like data set. And we usually say our data is a holdout testing set. And we say holdout means like we just don't ever use it for training. We don't do anything like cross-validation. We don't ever touch it. We basically only touch it until the very end when we're confident, like, okay, our model looks good. Let's do a final test to see how well did it actually do. So this is where we will have to be careful with making sure we don't have that cross-contamination, okay? Any general questions about training, validation, testing set? Yeah, okay. Yeah, so hopefully it sounds pretty straightforward. And again, that training and validation basically goes back and forth to allows us to train it and then kind of adjust and say, okay, well, it's not doing very well. And then the test basically saying, doing the final decision of saying, okay, did it actually work well? Note that your testing data should still come from the similar format as your training and validation. So usually we'll have like a huge data set and we'll split it into 3 parts. Validation, as we kind of saw, like a validation kind of like, we kind of did train tests, but really we'll talk about validation more now. Validation is kind of like about 20% of your data, give or take, you know, depending on how you're feeling basically and how good your model will be. With basically more data, the better. And then we'll keep our test data. We'll usually keep that very small because we don't need to like, hopefully if we have a large enough data set, we can randomly get enough data points from a small percentage of our data. And when I say big enough data, usually we're looking at least like a few 100,000, like that's probably ideal. The more the better for basically this kind of stuff, okay? So this leads us into our model complexity. So I kind of want to show you a little bit, basically, it's like when we have underfitting versus overfitting. So underfitting, you can think of like we have low complexity, we have high bias, low variance, right? Basically when we're seeing our, if we have an, if we're doing our training, I shouldn't say testing, but I guess testing's fine, but you can think of validation too. But basically our training error and our testing error, they're both large, basically. So not only is your training not doing a very good job, but then it's also when you try to apply it to your, what's it called, you apply the testing to your model, you say, oh, there's also, doesn't do a very good job, okay? This is kind of similar, well, okay, that's kind of like how we would test this out. And then overfitting is the opposite. Well, not opposite, but like a different, where we have very high complexity, we have low bias, but high variance, right? So basically we have this high complexity data. It's fitting it almost too well. It's basically trying to memorize the training. So our training error is very, very low. Basically it's memorized at all parts, but it does a really hard time generalizing. So its testing error is very, very high. So these are kind of like the difference between underfitting and overfitting. And we want something that's just right, like that Goldilocks zone. So we can actually kind of plot this out. This is a traditional graph that we have going on. Oops, from that more time. Okay, there we go. So this is a model complexity graph. It's kind of related to a ROC curve before, if you remember those ones from, I don't know, about a month ago now. But you can see here is that basically we have our test error, which at first, and this is the number of epochs. So at first our data, our model is very, very bad. It's underfitted. It doesn't have enough complexity. So it's doing a very bad job of getting training errors pretty low or pretty high, and testing errors pretty high too. And then as we basically increase the number of epochs, you expect the training error to get better and better and better, because that's the whole point of basically gradient descent. You're making it better and better and better and better for that training data. However, when we actually do the testing, which remember testing is supposed to be something that the model never sees, we're just kind of like using it to just see how well it does, you'll see that basically it'll get better and better and better, but then basically at a certain point, our training data, or our model is using the training data and memorizing it way too much, and our testing error actually increases over time. And so you'll traditionally see, like, if I were to draw this out really quickly, you'll tend to see like a curve that kind of goes like this for our training error. And then we'll also have, like, for our testing error, it'll kind of like dip down like this and then go up. This is like if it was continuous, but I just drew a few points, and these are just random points I drew, but the shape's the same. And really what we want then is we want something, we really want the lowest testing error, right? And so we actually want to catch it right about here, right? And so we would say, okay, about at the 150 epochs, or epochs, right? I'll pronounce it epochs because that's why I like it. But basically at the 150 epochs, this is like, this is the best model we'll really ever get, right? And this is where we want to catch this point. So this is actually something called early stopping. And so the idea here is that you would run this model and you would check it, let's say every 50 epochs, you would basically do a testing error. You basically take your model and say, all right, what's the testing error? And then what's the testing error after that? What's the testing error after that? And you basically would see where it falls across there, and that evaluates your best model. So essentially when you think about, like, when you're doing a number of epochs, you're basically making new models. Now the idea here is that you progressively get better and better. You get models that are better and better at your training data. That doesn't necessarily mean it's the better model though. So that's why we would say, okay, at a number of epochs we stop. There's some ways to avoid this too, which we'll talk about in a little bit. But this is one way we can do is basically through early stopping. Say, okay, like we stop it here. And this could even be like afterwards, you save the model every 50 epochs and you look back in the data, you're like, ooh, like this stuff over here is pretty garbage. We're gonna go ahead and go back here and just use this model and the weights. And when I say this model, same structure, just the different weights and biases that we have. Okay, so that's what early stopping is. And it's related to our model complexity graph right here. Okay, and I have a little note here too. We just stop early. Okay, yeah. So again, we're just trying to catch that right point. Okay, so cool. Any questions about that? Seem pretty straightforward. Yeah, it makes sense. Okay, cool. So the next parts are basically other things that we can have. So let's see here. Where is this one? Okay, whatever. So one thing is that one problem is that when the model goes bad. So when I think about this is that when the model is too confident, and we say the model is too confident when the has very, very large weights. And the reason why we say large weights means confidence is that basically it's saying that's like, oh, okay, like remember how we adjust our weights, right, with gradient descent and back propagation. Well, if our weights are very, very large, what will happen, it will either, if it's positive, it'll increase basically very quickly, or if it's negative, it'll decrease very quickly. So basically, it's saying like, oh no, this is definitely like when it does a lot, it's caught or it's lost. I'll say this is definitely in there. But the problem is if it's too confident that if it goes a new data point, it basically will increase that value too. So what essentially we need to do to make the model less confident is that we actually need to punish the weights, right? And we contribute this to the error function. So remember, when I say the model's too confident, the way it judges if it's right or not is based off its error function. So essentially what we're gonna do, we're going to adjust our loss function, or not our loss function, but adjust how we calculate our cost function to say, okay, when we have a large weight in there, we're going to punish that a little bit. And this is what these regularizations are. So we talked about regularization before, but we have L1 regularization, which is just really just using absolute value, and L2 regularization, which is using a squared value. So those are the two different ways we have it. And they're two different methods, and it actually turns out to be a few reasons why we want to do one over the other. So this is our general equation right here. And if you look back on this, you can actually see, for example, here's our cost function here. This right here is our loss function between each of our prediction, which is y hat, and yi is the actual, right? And we're doing this for each basically data point. We're feeding in the data points each time and seeing basically how well does it do. And this loss right here basically just says, how close are you to the actual value? And this is why very confident numbers, for example, if the number is like, you know, if it gets like 0.999999%, right, it probably is right, but the problem is that carries over to other points that maybe not be as right. So we actually add this little extra term, this lambda divided by m. Oh, I shouldn't, this is actually a typo, that's my fault. It shouldn't be, it should just be lambda. We're already dividing by 1 over m over here. You can see it written in different ways. So just know, basically multiplying lambda, which is just a number, essentially, times basically the absolute value of the weights. So basically, we're basically going through and saying, okay, for these weights, the absolute value of those, okay, add that to the function, or to basically the cost. So essentially, if you have larger weights, that means even though your error, let's say your error is like, your cost function is like negative 0.03, okay? Well, if you have down weights to it, it might be like negative or 1.3, something like that. So basically we're trying to increase that weight to say, okay, large weights, we want to get rid of that, okay? And then similarly for a squared value, which again, there's a typo right here. So I'm just going to delete this part. But the same thing happens with using L2 regularization, except instead of doing absolute value, we do W squared. So there's a couple of differences of why we would do one over the other. So one is that L1 regularization, basically we tend to get sparse vectors, and sparse vectors basically means that things tend to have small weights go to 0, okay? So basically you tend to have things that either have a value, like a relatively large value, or a value that's basically 0. So that's what we mean by sparse, okay? And this is actually, again, it reduces the number of weights. So this is actually kind of good, is that this basically will actually, well, depends on what you're trying to do. But basically we'll reduce the weight, because if the weight's close to 0, essentially that defeats the whole part of the node when we're actually making our neural network, right? So if you remember back from our neural network, and we have our different like lines, basically those line strengths are represented by the weights. So if we basically set the weight close to 0, you basically get rid of that pathway. So this is actually a really great thing for feature selection to pick out importance. So you can actually use this part to see what are the most important features that matter. Excuse me, I'm going to sneeze for a second. Thank you. Thank you. Allergies getting me today. But anyway, what was I saying now? Okay. Our feature, basically it's great for feature selection because it can pick out which ones are most important, because it drops all these weights. Turns out it's not that great for training though, because it takes a long time. These small weights can actually be a long time. So L2 regularization is usually what we'll use for training. It doesn't create sparse vectors. Its weights tend to be more homogeneous, which means like more or less the same, and they tend to try to make it smaller, okay? So kind of to show you the example of this is that we actually, again, this is better for training, but let's say we have two different vectors. They're like 1, 0, and 0.5, okay? And remember, we want the smallest value for our error. So just to kind of show you a little bit like what this would look like well, okay, like if I do the, let's say L1 regularization, well, we would do like, you know, the absolute value of 1 plus the absolute value of 0, right? And that's just equal to 1, okay? So that would be kind of the error. For L2 regularization, we would have 1 squared plus 0 squared equals 1, right? So okay, they have the same basically error for this vector, the 1, 0. But for the vector 0.05, like we're trying to figure out like which one should be used for these weights, 1, 0 or 0.5, 0.5. For 0.5, you can see if you do the absolute value, right? For L1 regularization, we just get the total loss to be 1. Okay. But in this case, if we were just looking at those parts, we would actually see for squared part, we get 0.5 squared plus 0.5 squared, which is 0.25, 0.25, that ends up getting an error of 0.5. So if we were to use L1 regularization, basically L1's like whatever. This one's just as good as this one, okay? However, with L2 regularization, say, oh no, I prefer the smaller one, the smaller loss, right? So actually it's gonna prefer this 0.5, 0.5, okay? And this is why the weights tend to go towards homogeneous, relatively small, and it actually is usually better for training because then we don't lose any of the values too for our weights. However, this one will tend to pick for other things. We'll tend to pick vectors that look like this, where we tend to have more sparse, basically. And this is great for feature selection. So those are differences. Generally, L2 regularization is really what you want, which is basically using this extra term here. And that lambda right there, this is a hyperparameter that we'll choose. We'd say, oh, we want to set this up to like 0.3 or, you know, whatever value that seems basically, you know, there's a whole bunch of things like what value to pick this. Usually it's just kind of like playing around with it and getting used to like what people use and what the research says. But the idea here is like you would have some small value to basically factor that part in the cost function. Okay, cool. Any questions about this guy? Cool. All right, awesome. So, oops, let me get back to my actual part. There we go. So that leads us to our last thing, which is dropout, which I think dropout is really interesting. I don't know if you've ever watched The Simpsons. Simpsons, the Homer here like has like a part where he basically ends up working out the same arm the whole time, and he goes with other shenanigans and stuff like that. And basically he never works out his left arm, so you can see his right arm basically like super huge versus his left arm here. So like you might know this when you work out, you need to basically, you know, cycle through basically your left and right? You need to kind of make those evenly out. This also includes probably like, you know, different parts of your body, right? You know, you got to think about like leg day. Like you can't just simply just do the same muscle group every single time to make it more even, basically more balanced. Well, our neural networks are kind of like the same thing, is that we don't want the model to basically retrain the same thing over and over and over again. And know that this is kind of like a self-perpetuating loop. If you always work out, let's say like you're always work out your right arm, right? Or let's say you're always lifting things with your right arm, but you never like, then your right arm's always gonna be stronger than your left arm. Because your right arm's always stronger, you're always going to lift more things with your right arm over and over again, which again makes it stronger. So kind of like as things get stronger, it makes things easier and easier for it to go through. Well, same thing happens with neural networks. You can imagine when we actually have our different, let me see if I don't know if I have, I can't remember actually if I have it. Good. So like you imagine like we have our little pathways right here, is that if you imagine if we had like a pathway that is like, if we say, okay, this one goes, oops, I need to draw. Where's my draw? There's my draw. Okay, so you can see like, okay, let's say this one for some reason, this weights, just maybe by pure chance, ends up being really, really strong. Okay, so it ends up being like, this is really, really strong. These are like relatively weak. Well, what's gonna happen is that this one's gonna dominate over these parts. Because remember, we're looking at like overall value. So if this layer, if this node is dominating everything else, then what's gonna happen is that basically these parts, these weights will go close to zero, and these will no longer have any contribution. Essentially, why do you even have them in there? Which again might say one thing like, okay, maybe we looking for importance, but for training, we actually want it to use the whole structure. We want it to more evenly. We want that complexity. By basically getting like rid of one or two of them like this, where like the main pathways are these things, we no longer have this complex of a model. And so you can see here, like basically getting rid of all this part right here actually gets rid of all of these extra little nodes, right? Basically, it's only going to each one of these four. So it's like, okay, we want that complexity. Otherwise, we're going to basically do some underfitting. So we can do something called dropout. And dropout basically gives it a chance. So this would be kind of like similar to like saying, okay, like on Monday, I'm doing arms. On Tuesday, I'm doing legs. On Wednesday, I'm doing some other muscle group and so on, right? And that's kind of like the idea here, except we do it more in a probabilistic kind of manner because we like probability. And the idea here, we'll usually give it some probability to say, all right, what's the chance of you actually dropping out? And what we might drop out is like, we're just not going to use you. Like, we say, okay, like each node here is going to have a 20% chance of just not being used this one round. So you can think of like your first like epoch, for example, like, okay, so like before you run the, basically run the feed forward, it's like, okay, are you going to be used? 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 So you can like imagine like rolling a die and say, okay, if it's the number 1, you're not going to be used. And like, okay, like you roll a die, oh, essentially you get 5, right? So like, okay, you're going to be used. Okay, it's like, oh, you rolled a 1, okay, you're not going to be used. Oh, you rolled a 1, you also won't be used. You will be used this time. And you feed forward through it, do the back propagation, and then you reset, and then you roll it before you do another feed forward with your epoch, you would basically re-roll the die. And so the idea here is that even though like we don't get to see all of them for every single epoch, we basically kind of force it to go down certain pathways just by pure chance. And if we do it enough times, eventually this will even out where everyone will get approximately the same amount of chance. And I say everyone, every node. Okay, so that's kind of what dropout is. And just know that's probabilistic, that basically it's just trying to figure out which one of, like, it's just randomly doing this so that way everyone gets a fair chance. So no one will hopefully dominate over the other ones. And you can also give dropout different parts of the layer. So for example, this could have each node have a 20% dropout. This one could have like 10% or a 40% dropout rate. And that means just that one row. So I'll show you some example code from like Keras. This won't actually run or do anything, but just kind of show you what it does. So we have our imports, right? Our dense model, our SQL, our sequential, and then our dropout. So this is kind of similar to what we saw last time. So we basically define our model here. We have our input layer, and you can see here, I have my dense layer, 128 units. Basically, that's how many different nodes we're gonna have in. We have our input dim, there's gonna be 100 basically here. This is just random stuff, right? And then we have our ReLU, or activation of ReLU. And then also I just gave it a name just to make it easier to track. And then also have this dropout here. So basically we would add this dropout, and this dropout would basically, okay, there's a 20% chance that every node, every 128 nodes, there's a 20% chance that it won't be used in this round going forward. And then you can see I have another layer here, 256 nodes, and this one has a 20% chance that each one of these nodes could potentially be used or not, okay? And then of course I have the very end, so our softmax and our final output layer. So just kind of showing you what this looks like, which is nice that it kind of gives a little quick output right here. So you can see here basically is that we can actually have the dropout as part of our network. And the way I kind of think about this, it's really trying to connect these two together, okay? Basically the dropout's describing how often should you drop out from here, okay? And note that I could have also given it like 0.1 or something like that. There's not a reason why I have to do it that way. So anyway, that's dropout. Cool. Any questions on that? All right, awesome. Asad, did you have something?
Yeah, I think, so for dropout, it's just like the same idea of where you're partitioning the data and kind of running through it.
Yeah, it's kind of like batches, but I guess you could say think of like that. It's kind of like batches, but for nodes. You essentially are saying like, here's your full structure, but for each epoch you're running it through, you're going to basically randomly take out nodes. So it's like, oh, you can't go through this node. We'll freeze the weight. We'll basically freeze the weight on that one node, so it can't be affected. And that way, it'll have to use the other parts. So it'll actually use less complexity. But the idea there is that because we're going to randomly do it every single time, it will overall be a more well-rounded model.
Okay, and then like, I guess we haven't really looked at it in depth code-wise, but like, so does it do that and then it kind of just puts everything together?
So yeah, well, it's kind of interesting. So like basically for the first epoch, so let's say for dropout, let's do a little scenario. So let's say we have our input here on this model. Okay, and I'll go ahead and start drawing on this. And then we have our dropout that says, all right, this part of the code, this node is not going to be used. And then we do a dropout here. Let's say these two nodes, just by chance, are just not going to be used. Okay, so what ends up happening is that this ends up being something that looks like, basically you can only use the pathway going from here to here to here. So you can see all the stuff in blue basically is what I can actually go through. So basically it completely skips over. And so when you feed forward, it will only go into the nodes that actually have, it's like we're almost creating like a new network, but we're using the values that were already in here. So the important part basically is to realize is that, okay, like we're only using like, let's say this node, or sorry, that's not a node, this node, and this node And then for the second layer, this node and this node. Basically, we essentially have a new network, but we're going to update the weight. So basically these weights aren't going to be updated. So if I actually write this probably in red, it's probably better. Let's do red here. So if I write this node's not going to be used, this node's not going to be used, this node's not going to be used. So basically it's just having a more simple structure, but the weights are not going to, like, we're basically every time we're doing a feed forward and back propagation, we're just adjusting the weights a little bit. So on this round, these weights will be updated however the model goes forward. And then these weights in here will just stay constant. And then when we start the second round, we'll basically redo the whole thing and say, okay, which node should we use? Okay, well, in this case, we're not gonna use this node. We're not gonna use this node again. We're not gonna use this node. And then these weights won't change. They'll basically be frozen. It's not gonna be part of the model and we'll only run this part. So essentially each time it's being used, the weights will be updated and the biases will be updated. Hopefully it's like the next round is that, or some of future rounds, they'll be included in the next part and their weights will be updated the next time. So essentially you don't have to like worry about like including it. It's just like each time you do the epic.
Okay, so the 20% chance is applied at each back propagation.
Yeah, or it's technically the feed forward, like because it's when, yeah. So okay. It's the feed forward part. And then basically when you do the back propagation, only the weights of the nodes that were used that round will be updated.
It'll go back, it'll reapply, and then it'll pick new nodes. Okay.
Yeah, and that's kind of like, and that's the way, like you were saying, like, oh, do you add it up at the end? It's kind of like, oh, you essentially are just updating it every single time. So there isn't anything to do at the very end. Okay, cool. All right. So that's those are some ways basically we can basically avoid overfitting, basically get more evenly. We can think of this like optimization stuff. Okay, and then this is the nice code. Like you can see adding a dropout layer is not super difficult. There is some controversy sometimes with like whether you should use a dropout, like and stuff like this. And it's kind of funny is that kind of like a lot of things in machine learning right now, deep learning is still like in a lot of research of saying like what exactly, how do we do the things we do? And it's not always super clear what we should do. And so a lot of times you use dropout because it works. And it makes sense. I mean, it makes sense that hopefully that you're like trying to get the model to use more complexity versus lower complexity, basically using the same pathway over and over again. Okay, cool. Okay. So that's going to lead us to optimizations.